This video is on islands of stability. So islands of stability is a term that is often used both in terms of nuclear stability as well as electron configuration stability. We're going to be looking at the electron configuration stability kind. And the basis is that certain electron configurations resist changing and reacting. And remember that one of the golden rules in chemistry is that substances will change if that change results in greater stability. In other words, if something doesn't change, then there must be something inherently stable about it. And one of the things that we've noticed in these electron configurations is that there seem to be electron configurations that are associated with elements that show an unusual degree of stability. First and foremost is the S2p6 electron configuration. The S2p6 electron configuration, as you know, is the noble gas electron configuration. All noble gases, with the exception of helium, have as their valence electron configuration S2p6. Their last electrons in the highest energy level are in an S2p6 conformation. The next thing that we notice, however, is also a D10. So anything that has a D10 electron configuration, S2D10, S1D10, and just plain old D10, has an electron configuration that is unusually stable as well. It resists change. And we see this in the elements that are on the periodic table. So these are the noble gases, used to be called inert gases, because they would not react. Even under regular circumstances, they do not react and they do not form ions. The zinc column. So zinc, cadmium, and mercury very rarely react on their own. They need to be coaxed into reacting in highly acidic situations. That's one reason why we coat things with zinc, called galvanizing things. Copper, silver, and gold are also fairly non-reactive. That's one of the reasons why we like to use them in jewelry and in other decorative elements, because not only are they shiny, but they don't lose that luster, they don't corrode, they don't rust. And it is for this reason that we believe that the copper, silver, and gold column adopt an S1D10 electron configuration. Slightly less stable is the D5 electron configuration, which is the manganese column. And chromium column seems to show that promotion as well. And then finally S2p3. Now S2p3, which is the nitrogen column down to arsenic, does react, but in comparison to carbon and oxygen columns that flank it, there is this well of stability. So the islands of stability aren't saying that there isn't going to be a reaction. It's just that in order to form an ion, in order to bond, in order to change what it's been doing, it needs to be coaxed to do that with a greater amount of energy than one would expect, given its trend, its placement in the periodic table.